come here. Coyote Peterson's on.
Hey guys, I'm Coyote Peterson, and today we're back at it again, hunting a bear. Now y'all see that one over there? Now we must be very quiet so the bear doesn't hear us. Oh wait, what's this Y doing here? This is my X initial. This is my X final.
Sophia, I don't really understand what they're talking about.
Don't forget to
Oh, don't worry, I'll show you.
now more of these videos.
Coyote Peterson shot the gun from a certain height, Y, and then there's going to be a gravitational pull going downwards, which is G, which is also acceleration. And then there's a certain time it takes to get to the ground, which is T. The horizontal component consists of X final, which is your final distance at which the bullet lands at, X initial, the starting distance from which the bullet was shot at, the velocity, which is constant the entire time, and then the T from the vertical component from which it hits the ground.
Okay, but then why do we even have 1/2 AT squared inside the equation if this is only in the horizontal direction?
Well, we actually don't, because A would be 0 because this entire equation is constant. Hey, Mikaela, come here.
Wait, hold on, I'm coming.
It says to find the Y. Can you find the Y?
Oh look, it's right there.
Now it says we need an A.
Oh look, here's the A that we need, Sophia.
Wait, so what does this tell us?
Here's Y, the height of the tree.
Here's A, how fast the orange was accelerating, but it can also be replaced with G, gravity. And here's T, the time it took for the orange to fall off the tree, which then gets squared.
Well, you did very good on your drive today. I just have a few things I need to tell you. So I noticed that your speed kept on going up and down during the entire ride.
That's because there was a lot of friction on the road. It was super rough.
Well, when you were on a smoother surface, did you think it was easier?
Definitely.
Well, that's because there's going to be less external forces and negligible friction.
Wow, how does velocity even work?
Well, why don't we go back inside and I'll show you how.
Thank you.
Our velocity is equal to the change in x divided by the change in time. Our change in x is measured in meters, while our change in time is measured in seconds. Let's do an example. Well, if we look at the first graph right here, it shows that the velocity is through the slope of a position versus time graph. If you drive 8 meters for 4 seconds, your slope will be 2 meters per second. And then if we look at the second graph, if you drive 4 meters for 2 seconds, your velocity will also be 2 meters per second. In both cases, the slopes are the same, meaning that the velocity is going to be the same. A straight line in both of the graphs means that they have a constant velocity.
Alright, so the kids are complaining, they complain the first day.
Let me see how much time I have left. Oh no, I'm gonna be late to class.
Ding, ding, ding.
The distance that I walked from this classroom all the way over to this classroom was 42.19 meters.
The displacement she had from the starting point to the end point was only 28.19 meters.
The distance that you travel from here all the way to here is not the same as your displacement from here to here. Your displacement is measured by your starting point and your ending point, while your distance is measured by the path that you took, not necessarily from starting point to ending.
This is my X initial. This is my V initial.
Oh look, here's my X final.
In this clip, Sofia and Mikaela are playing with football. This shows projectile motion because you have a horizontal and vertical component.
when Sofia kicks the ball to Mikaela. This can be demonstrated with these two equations.
This demonstration shows displacement. We would first start off by walking 5 meters north, and then turning back around and walking 5 meters south to get our displacement as 0. This demonstration correctly explains displacement because we started here and then we went 5 meters north, then we turned back around, went 5 meters south. Our distance would be 10 because it's a scalar quantity, meaning that it doesn't need a direction, while our displacement is a vector, meaning that it needs direction. So if we went 5 meters north, it would be positive, and if we went 5 meters south, it would be negative. A positive 5 plus a negative 5 will give us 0, meaning our displacement is 0, but our distance is 10 because it doesn't matter about the signs.
In this demonstration, we'll show constant velocity. We have a measuring tape at every 0.5 meters. In this demonstration, we show constant velocity. We recorded a car going from 0 meters to 2 meters, and each 0.5 meters we had a tape. To find velocity, you have to use change in x over change in time. X is meters, and then t is seconds. For 0.5 meters, the video said it was at 1 second. At 1 meter, it was at 2 seconds. At 1.5 meters, it was at 3 seconds. And at 2 meters, it was at 4 seconds. If we were to solve for all of these, you'd get 0.5 meters per second each time. And if you were to put this on a graph, you would get a straight line like this. A straight line means that you have constant velocity. This demonstration will show projectile motion.
This demonstration accurately shows projectile motion, which is traveled in a parabola shape. In the projectile motions, we have horizontal and vertical components. These are independent from each other except for our time, because when it hits the ground vertically, our velocity is going to stop. In our horizontal direction, velocity will be constant, but we will get to that later. So our y final is whenever it hits the ground. Our y initial is where we start from. Our velocity initial we would find by using sine theta to find velocity inside the y direction. We would add it to 1/2 at squared to find t. Our a is going to be 10 because gravity will be constantly pulling it down. Once we find our t, we'll plug it into our horizontal components here. To find our x final, our x initial will be here where we started at. Our velocity we'll find using cosine theta. We'll plug in our t where we got from here, and then we'll find our x final.
This is a horizontal projectile motion demonstration that can be done in class.
The x final will be the distance that you're looking for at the end to land inside the cup. The x initial is where you started rolling the ball. Then you have the velocity, which can be found from rolling the ball from the starting point to a certain point before it falls the table to get a distance and divide that by the time it took to roll. Then you'll get the velocity and you'll multiply that by the time that you got from the vertical component to get x.
The end!